It has been estimated that within the observable universe, there might be as many as a septillion stars. While each of them is far larger than the Earth, they all differ in terms of age, size, color, and composition. Despite being very far away, we know a surprisingly large amount about them through observation and an understanding of the basic units of matter. Learn more about stars, how they're born, and how they die on this episode of Everything Everywhere Daily.
This episode is brought to you by Rad Power Bikes. What does getting outside mean to you? Is it going for a walk, a run, even a bike ride? What if that bike had a motor on it and allowed you to pedal or throttle to your destination? Even if that destination is simply getting back to fun. Rad Power Bikes designs electric bikes that let you do just that. They empower riders of all types to discover biking's benefits. Schedule a test ride today at radpowerbikes.com.
When humans first looked up at the night sky, they could see lights, but they had no clue what they were. The first theories held that they were either holes in the firmament with light shining through, or that they were lights that were somehow fixed in the sky, except for the fact that there were a few of those lights that actually moved. Whatever they were very clearly different than the sun and the moon. Except that some ancient Greek and Islamic astronomers thought that the stars might just be the same thing as our sun. This idea was revived in 1584 by the Italian astronomer Giordano Bruno. Bruno not only thought that the stars were like our sun, but that they also had planets like Earth and possibly people just like us. His theories were mostly rejected by his contemporaries, and he was later tried for heresy, but within a century, the idea that the stars were like our sun took hold. But if the stars were like our sun, then what exactly was the sun? For the longest time, people thought that the sun was a ball of fire. And to be honest, it wasn't a totally unreasonable assumption given what people knew at the time. It was hot like fire, and it was a similar color to fire. As science advanced and we learned more about things like heat, energy, and the size of the sun, some things just didn't add up. One 19th century scientist in particular, Hermann Von Helmholtz, tried to figure out what made the sun give off energy. First, he assumed that the sun was on fire, and it was literally undergoing combustion just like a fire burning coal as its fuel source. After doing the math, he realized it would burn out relatively quickly, in about 1,500 years. This didn't square with even the biblical theories which held that the Earth was only 6,000 years old, let alone the evidence mounting from geology which said that the Earth was millions of years old. Another theory he came up with assumed that space was filled with matter, and that matter was constantly crashing into the sun, which was responsible for the endless supply of heat. However, that also didn't pan out, as it would require 100 trillion tons of mass to slam into the sun every hour to produce that much heat. A final theory was that the sun was constantly shrinking. He estimated that the contraction of the sun by its enormous gravity would provide the energy to make it shine. He calculated that the sun would only have to contract in diameter by 1 inch or 2.5 centimeters every 3 hours. This at least got the sun to a point where it could shine for millions of years. However, the theory still had problems. It would mean that the sun was once much larger, and that it was constantly getting smaller. It also didn't jive with the age of the Earth. Nonetheless, this was the accepted theory for much of the late 19th century because there wasn't anything better. There must have been something else that was making the sun give off energy that answered all of the outstanding questions, but no one knew what it was. Around the same time, the science of spectrography was developed. Through spectrography, it was discovered that elements gave off very identifiable spectrum of light when heated. From this, it was possible to analyze the light from the sun, and it was determined that it was mostly hydrogen and helium. So the sun was made of the same stuff we had on Earth, but it was producing energy from some unknown method. In 1904, Ernest Rutherford posited that it was radioactive decay which was producing all of the heat. Things became clear when Albert Einstein published his famous E=mc² equation. That stated that mass could be converted into energy. A lot of energy. Enough energy that the sun's energy output might just start to make sense. The guy who put it all together was a British astronomer by the name of Arthur Eddington. Eddington wondered what was happening inside the core of the sun. He calculated what the pressure and temperature would be deep inside the sun's core. He realized the pressure would be enough to turn hydrogen into a solid, and that the temperatures would be almost 27 million degrees Fahrenheit or 15 million degrees Celsius. At those pressures and temperatures, it was enough for the hydrogen atoms to fuse together to create helium. The source of the sun's energy, it turned out, was nuclear fusion. Since Eddington's theory, there has been a great deal of experimental and observational evidence, both of the sun and other stars, such that we now have a pretty good idea of how stars are made and what happens to them. So, what exactly is the process? It all starts with hydrogen. As I mentioned in my previous episode on hydrogen, the vast majority of all matter we can observe in the universe is hydrogen. A star will start out as a massive cloud of hydrogen and a small amount of helium. All other elements are in such small amounts that I'm going to ignore them for the purposes of illustration for the rest of the podcast. Even though the hydrogen is in the form of a very diffuse gas, it still exerts a gravitational force. Over time, this gas can coalesce via gravity into a massive sphere. There are astronomical images of nebulas that are known as the Cradles of Stars. These are massive clouds of gas where stars are produced. The key thing in the life of any star, and the thing which will determine how hot it burns and how long it lives, is its mass. Mass means everything for stars. Paradoxically, the more mass a star has, the shorter its life. More on that in a bit. As the hydrogen sphere begins to contract, the pressure becomes greater, as do the temperatures deep inside. Eventually, if there's enough mass, the temperatures and pressures will be enough that fusion will occur. Hydrogen atoms will be fused to make helium, and it will give off a tremendous amount of energy. The amount of mass which is necessary to start fusion is approximately 7.5% the mass of our Sun, or about 80 times the mass of Jupiter. A star without enough mass to start fusion is simply called a brown dwarf. Stars with about the mass of half of our Sun or less are called red dwarfs. These are the most common types of star in the universe, and they can be exceptionally long-lived, living for trillions of years. One question that was raised early on was, what stopped a star from continually collapsing inward due to gravity? The reason why the size of our Sun is relatively stable has to do with something called hydrostatic equilibrium. Matter expands when heated. While gravity is pushing inward, the heat of the matter inside the star pushes things outward. If the star keeps contracting, it will accelerate fusion, creating more heat, expanding the star outward until it reaches an equilibrium. The energy which is being released inside of a star can take a very long time to reach the surface. A photon released near the core might take as long as 10,000 to 170,000 years to reach the surface. This is mainly due to the density of the matter that it has to go through. I actually mentioned that larger stars burn quicker. This is due to gravity. The more mass a star has, the greater the gravity, the more fusion will occur, and the faster it will burn. The mass and temperature will also be reflected in the color of a star. Astronomers have developed a classification system for stars according to their color and temperature. The coolest stars are red, and the hottest stars are blue. Going from hottest to coolest, the classifications are O, B, A, F, G, K, M. This is known as the main sequence. It sounds rather out of order, but there are several other mnemonic devices for remembering it. The classic one is O be a fine girl or guy, kiss me. But there are many others, including Overseas Broadcast, A Flash, Godzilla kills Mothra. With each letter category, there are also numbers. Our Sun is classified as a G2 star. A G-type star can burn for billions of years. O stars are the hottest and are blue. They are the rarest stars in the universe because they usually aren't around very long. An O star might only have a life of a few million years before it explodes as a supernova. Our Sun turns 600 million tons of hydrogen into helium every second. Even though the Sun is really big, the amount of hydrogen is finite. So what happens when it runs out of hydrogen? Then helium starts to fuse into carbon. This is a multi-step process known as the triple alpha process, as helium has 2 protons and carbon has 6. When this happens, our Sun will turn into a red giant. The core condenses, which is necessary to get enough pressure to fuse helium, but the upper layers will expand from the heat. What happens when there's no more helium? The fusion of heavier elements will continue depending upon the mass of the star. If there isn't enough mass, the fusion will eventually stop because you need more pressure to fuse heavier elements. Regardless how big the star is, however, there's a limit. If you remember back to my episodes on uranium and plutonium, you can get energy by splitting those large atoms via nuclear fission. You can get energy from light atoms like hydrogen via fusion. There's a point in between the light and heavy elements where you will no longer get energy from fission or fusion. You need to put energy into the system to split or fuse atoms, and no energy will be given off. And that point is the element iron. Once a star is left with iron, it's game over for fusion. At that point, the star will no longer produce heat from fusion, and there isn't any stopping the star from collapsing inward. What happens next will depend on the mass of the star. The end fate for our sun is what's called a white dwarf. It will lose much of its mass in the process, but it will shrink down to a very small size. The only thing stopping it from collapsing further is something called electron degeneracy pressure. The best way to describe electron degeneracy pressure is that the forces inside the atom are literally the only thing preventing the further collapse of the star. For a white dwarf to be created, it has to have 1.44 solar masses or less. This precise limit is known as the Chandrasekhar Limit, named after the Nobel Prize-winning physicist Subrahmanyan Chandrasekhar. If a star has a mass greater than the Chandrasekhar limit, electron degeneracy pressure will be overcome. The forces inside all the atoms will cause the electrons to fuse into the protons to become neutrons, and the whole star will become a neutron star. Neutron stars are incredibly dense. Imagine stars larger than our sun condensed down to only 10 kilometers or 6 miles in diameter. They're like a gigantic atomic nucleus. The thing preventing a neutron star from collapsing even further is neutron degeneracy pressure. This is the very force of an atomic nucleus keeping it from collapsing. However, this too has a limit. If the mass is more than about 2.1 solar masses, it passes the Tolman-Oppenheimer-Volkoff limit, and at that point, there are no known forces in the universe that can support the star, and it becomes a black hole. The process of collapsing into a white dwarf, neutron star, or black hole can result in a supernova, which is what happens if a star is about 10 times the mass of our sun. This happens from the shock wave from the collapse, so the resulting body has only a fraction of the matter of the original star. The rest of the mass is explosively expelled outward. There's one final stage that might theoretically exist for white dwarf stars, and that's known as a black dwarf. When a star collapses into a white dwarf, there's still a lot of residual heat even though there's no more fusion. Over time, a very long time, all of that heat will eventually dissipate, and the result will be a very dense body that is cold. This is theoretical because the time it would take to cool down to that level is longer than the current age of the universe, and if they did exist, they'd be impossible to see. Stars are the engine that drive the universe. Our sun is responsible for all life as we know it. All of the heavy elements, energy, and fantastic stellar objects that we know of all came from stars. And the stars are just the result of incredible amounts of smushed together hydrogen. Everything Everywhere Daily is an Airwave Media podcast. The associate producers are Thor Thomsen and Peter Bennett. If you'd like to support the show, you can do so over at patreon.com. And remember, if you leave a review or send in a question, you too can have it read on the show.
We have witnessed the life cycles of the stars. They are born, they mature, and then they die. As time goes on, there are more white dwarfs, more neutron stars, more black holes. The remains of the stars accumulate as the eons pass. But interstellar space also becomes progressively enriched in heavy elements, out of which form new generations of stars and planets, life and intelligence. The events in one star can influence a world halfway across the galaxy and 1 billion years in the future.